All right. Hello, AP students. Welcome to your Intro to Stoichiometry pre-lecture. So you guys have been working with balanced chemical reactions and identifying the type of reaction. And now what we're going to start getting into is, well, how do we quantify these reactions? How do we quantify in lab this ingredient recipe, this recipe of reactants to create this desired amount of product into a way that we can actually now predict numerically how much we're going to get, how much we need, right? So the important thing to realize is that the balanced chemical reactions actually provide, all right, the what we call stoichiometric ratio, and I misspelled the stoichiometric metrical or molar relationship, okay, between chemical species in a reaction. All right. So essentially, that's just a really fancy way of saying that those coefficients that we put in front of a balanced chemical reaction in order to observe the law of conservation of mass are equivalent to saying that they are our ratio in moles of how much of each chemical species we need, right? And therefore, because we have an equivalence, we can say that we are now provided what we call molar conversion factors or molar equivalents. And I'm going to actually just write equivalents. All right, that we can then do dimensional analysis with. And dimensional analysis with the mole from the balanced chemical reaction is stoichiometry. So stoichiometry is the process, okay, of relating chemical species, okay, in a balanced reaction via the mole, okay, via the mole or specifically the molar ratios revealed through the coefficients, okay? So let's just do a quick practice problem. This is very, very basic, okay? So we have some amount of carbon reacts with sulfur, an allotrope of sulfur to produce carbon disulfide, okay? And when we balance it, we would get, of course, this very basic, okay, uh, four, and then boom, one, okay? And I'm just gonna write one for the sake of the next thing I'm going to do, but technically, remember in balanced chemical reactions, we don't really write one, it's just unnecessary, okay? But here's why we care about this, okay? Let's put it now into a word problem. Like, what am I actually saying? Am I just saying there's one way to say this, as I could say this as, well, for every 4 atoms of carbon, I need 1 particle of sulfur 8 to produce 4 particles or molecules, however you prefer to say it, of CS2. And that's great. That's actually kind of what it's telling us. For every 4 and 1 of this, I get 4 of that. But remember with chemistry, it doesn't really help us if you can't turn it into, I don't know, a sellable product. You can't turn it into a macro scale amount that we can create in lab, measure in lab, and then produce, right? For money, okay? And so what we need to understand is that this is again where the mole is so important. It scales up our understanding, specifically quantitatively, when looking at particles to a size or a proportion that is actually relatable to us. And so another way we can say this is for every 4 moles of carbon and 1 mole, okay, of sulfur 8, I produce, okay, or we or whatever produce 4 moles of CS2, carbon disulfide. Okay. And that gives us something that we can tangibly do something with in lab. Because remember, if we can figure out the mole ratio, the mole amount between relative chemical species, we can figure out the grams using molar mass. Okay, so now it becomes really valuable to us. Okay, we could also say this in another way. If you want to flip it around, we could say to produce 4 moles of carbon disulfide, I require, all right, 4 moles of carbon and 1 mole of sulfur allotrope. Okay, sulfur 8 allotrope. All right. Both are saying the same thing. Both are using the mole and particularly the molar ratio revealed in the balanced chemical reactions to offer me a tangible macro scale understanding of what is this actually giving me that I can do something with. So let's go through a couple example stoichiometry problems and then we'll be kind of done for the day. So if you react 2.5 moles of carbon, how many moles of carbon disulfide can you make? All right, so just like with any unit conversion, we start with what we know, all right, and we create a little map for ourselves. So what's the map? We want to get from 2.5 moles of carbon to moles of CS2. All right, so that's my map. So I'm going to start with what I know. So I have 2.5 moles of carbon. And I say, well, I'm staying in the same unit of measurement, moles, but what's changing is my substance. So now I'm treating substances like a unit. So we're treating the substance or the species, the chemical species, like a unit where we can cancel it out. Okay, we're going to cancel out our old substance and replace it with a new substance. So I'm going to say, well, how do I know what standard equivalent relationship exists between carbon disulfide and carbon? Well, I look above and I say, oh, well, my chemical reaction tells me, according to this particular, okay, reaction type, synthesis, I need 4 carbons to produce 4 carbon disulfides. So I can turn that molar relationship into an equivalent, which is therefore a unit conversion. So I say, okay, well, I know from my balanced chemical reaction that between these two species, for every 4 moles of CS2, I get or require 4 moles of C. And what happens is I cancel out my substance and I'm left in moles of CS2, which is, by the way, exactly where I want it to be. And I'd get a value of course, 2.5 moles of CS2. And you're like, I didn't need to do that. I didn't need to do that. I could have done that in my head. Sure. Awesome. In the future, it will be far more complicated. So I wouldn't do it in your head, at least initially, because what I'm trying to teach you is what is the actual process in your thinking that is allowing you to take these very simple examples and allow you to build up and upgrade them to more complex settings. Again, still applying the simple concept in the beginning, right? A lot of chemistry is, let me introduce it to you in a very simplistic method so that when you see it more advanced, you don't get all frazzled and you just remember, oh, this is technically totally the same thing that I've done that's super easy. I'm just using bigger numbers or I'm just doing more steps of it, right? So now that we have moles though, of course, that's a really helpful information, but not super helpful from your lab because we don't exactly measure things in moles in lab. So what we would do is now we ask ourselves, well, then what does this translate to gram wise? So if I have 2.5 moles of CS2, okay, I just am going to multiply my molar mass, our very familiar conversion, right, to get to grams that I can now use in lab. So the gram amount is about 76 grams per mole for CS2, okay, giving us a value where we cancel out our units and we're left in grams of CS2, giving us a value of approximately, I think I'm a little bit off, but 190 grams of CS2. All right. And it should be in 2 sig figs. All right. All of our answers should be in 2 sig figs, given that we were given a value of 2.52 sig fig. Okay. And so that's what we do. So, go ahead and take a moment to try the next problem on your own. All right. And I should mention that the word excess here is quite important because what it means is that the amount of product form is going to be determined by then the silver nitrate. Okay. The amount of solid product, AgCl precipitate form, is going to be determined by silver nitrate. And so oftentimes when you see the word excess in a problem, what it's trying to tell you is that you can rule out the effect of calcium chloride on determining your amount of product made. All right, that's all it's really saying. But go ahead and take a moment to balance this chemical reaction, this double displacement precipitate forming reaction between the 2 ionic compounds of silver 1 nitrate and calcium chloride. And then try to answer the question using stoichiometry. And then I'll walk you through it in a second. Okay, so hopefully you pause me and let's go ahead and go through this together. So the values you should have gotten balancing wise are 2. I'm just going to write in the 1 for now. 1, but again, final answer, you don't need to. 2 and 1. All right, that's how you would balance it. We have a problem where we're being asked what from 3.50, 3 sig figs, okay, grams, 3.50 grams of silver nitrate. Okay, how many grams of precipitate, AgCl, are formed? All right, so that's where we're going to go. Notice we have a grams to grams and a substance change. Whenever we see, oh, gee willikers. Whenever we see a grams to grams, you have to remember you have to go through the mole. Okay, we cannot translate from just grams to another grams because of density and issues of grams being really inconsistent when we're using it as a standard between 2 different substances. So we're going to have to travel through the mole before we can go to grams of another substance. All right. So we are technically changing both units and substance in this problem. So this is going to be a longer process. So what you should have gotten is you should have, of course, started with your what you know. So you know 3.50 grams of AgNO3. And then you're going to convert it using molar mass because you got to get to moles. So using molar mass, you're going to turn this into a mole value. So we say for every 1 mole of AgNO3, I have 169.88 grams of AgNO3. That's going to give me moles of AgNO3. Once I'm in moles of AgNO3, now what I can do is I can say, well, I need to convert between AgNO3 and the new substance AgCl, because once I've gotten to moles, moles unlocks the door for me to use my molar ratios revealed in my chemical reaction, my balanced chemical reaction. So I'm going to use 2 and 2. So I say for every 2 AgCl, I have 2 AgNO3. And what I'm left in, of course, then is, I should be canceling this out as we go. I'm left in, okay, moles of AgCl. Okay, awesome. So I've done this process where I've canceled out old units and old substance. And now I just got to make sure I'm in my preferred new unit. So I say, well, I know that for every 1 mole of AgCl, I have about 143 grams of AgCl. And that allows me to cancel out moles of AgCl. And I'm just left in grams of AgCl, which is, by the way, exactly what I wanted. So then what we do is, imagining that this is over 1, we multiply across top 3.50 times 1 times 2 times 143 divided by parentheses 1 times 169.88 times 2 times 1. And we get a final value of approximately 2.95 grams of AgCl should be produced from 3.50 grams of silver nitrate, as long as we have excess calcium chloride, allowing us to say that AgNO3 is what we call our limiting reactant, or our reactant that determines how much we actually can get as a product. Okay. So go ahead, and we're going to try now using the 22.4 molar volume and molarity as also a stoichiometric step in our quantification of reactant species according to a balanced chemical reaction. So what we have here is we have a similar problem. What mass of nickel reacts with all the silver nitrate in a 1.25 liter of 0.15 moles per liter molarity solution? So if you're like, wait, how is this stoichiometry? Well, basically stoichiometry is anything with a mole and a balanced chemical reaction. So we're already seeing that we're meeting those qualifications through molarity, right? And then we have the reaction below. And what we see is this is a single metal displacement reaction, okay? Nickel is kicking out silver, which means nickel must be more reactive to nitrate than silver is as an overall metal. And so what we get is we'd have to balance, of course. So when we balance, we say, okay, we're going to find that we need 1 nickel for every 2 AgNO3. That produces 1 nickel nitrate for every 2 Ag solid. Okay. And what this reveals to us is, let's try to explain this for a second, is it tells us the following, that via verbiage, I need for every 1 nickel, or 1 mole, I should really say 1 mole of nickel and 2 moles of silver nitrate, we produce 1 mole of nickel nitrate and, okay, and I should be specific, nickel 2 plus nitrate, right? Nickel 2 plus, and 2 moles of silver, solid silver, okay? And so what that means is, okay, that's the relationship. That's the molar ratio we have. And according to our problem, we want to get from a 1.25 liter sample of silver nitrate, a 1.25 liter sample of silver nitrate, 2 grams of nickel, okay, required. So what we're going to do is, that's our little map to make sure that we stay in line, right? And we're going to say, all right, well, let's start with what I know. So I know I have 1.25 liters of AgNO3. But we know from stoichiometry that liters of one substance to grams of another is not an easy transition. Like, we don't have a singular, Avogadro's number that takes us there. But what we are given is the molarity of that silver nitrate solution. So what we can say is, well, I know I need to get to moles in order to transfer or change from one substance to another, from AgNO3 to nickel. So how do I get to moles? How do I get this solution of AgNO3 to moles? And I can say to myself, oh, well, the molarity offers, all right, a conversion factor. It's an equivalence of itself, relating moles and liters for this particular solution. So we say, well, I know that for every 0.15 moles of AgNO3, I have 1 liter of AgNO3. Okay, so that leaves me with now moles of AgNO3 And if I'm now in moles of AgNO3, now I'm able to use my molar ratios revealed in my chemical reaction, my balanced chemical reaction, to then go from moles of AgNO3 to moles of nickel. Again, never jumping straight from one substance to another unless we've gone through the mole, right? And so what we say to ourselves is, okay, next step, well, I know according to my balanced chemical reaction, for every 2 moles of AgNO3, I require 1 mole of nickel. Okay, for every 2 moles of AgNO3, I require 1 mole of nickel. All right, so that leaves us with now, one or some moles of nickel. And then I look at my question and it wants me to report it in grams. So I say, well, for every 1 mole of nickel, I know there's 58.7 grams of nickel. And that gives me my final, okay, answer in grams of nickel. And then of course, what I do is I pretend this is over 1. So I multiply all my numerators across 1.25 times 0.15 times 1 times 58.7 divided by parentheses 1 times 1 times 2 times 1. And I get my final answer is that I produce require, 5.5 grams of nickel in order to produce or react with the 1.25 liters of AgNO3. Sorry, not produce, but react with. And that is how we could use molarity in a stoichiometry as well. Again, tying in the molar ratios revealed in the balanced chemical equation, but using molarity to get me to initially what the unit I need for my given species. Okay. So we can do the same process using molar volume with gas-based reactions. So remember that molar volume at standard temp and pressure is 22.4 liters for every mole of gas. Or another way to say it is for every mole of gas, I take up 22.4 liters of space. So what we see here is an example reaction, okay? And it kind of gives you a general idea. I'm going to actually let you read through this yourself. And what I'm going to say is that tomorrow, you should come ready with the answer to this. And when you look at my PDF, I will upload the answer tomorrow once we solve it together. So go ahead and try this problem out on your own. And you, of course, if you're on a digital version, I did hyperlink the solution because it's sourced from some website. I think it's a Chem Purdue question, but give it a try on your own using the similar concept of how we applied molarity in stoichiometry. You're now using molar volume in stoichiometry. So good job, you guys. And then tomorrow we will walk you through some more stoichiometry problems in relation to more AP word problems. So good job and best of luck.